The next reaction that we are going to talk about is acid catalyzed hydration. So when we are talking about hydration, we are thinking about water. Therefore, we are going to add hydrogen and OH across the pi bond. So the reaction is acid catalyzed because that acid acts as a catalyst, so it will lower down the activation energy and the reaction will go faster. So we are using this catalyst, and this catalyst is not consumed in the reaction, so we are going to get it back at the end. Now, if you look at the mechanism for this reaction, this mechanism involves formation of a carbocation. So again, similar to hydrohalogenation, we need to consider the possibility of the rearrangement. Also, addition of hydrogen and OH across the pi bond follows the Markovnikov rule, meaning that hydrogen will be added to the less substituted carbon and OH will be added to the more substituted carbon. The acid source here is sulfuric acid. I talked about concentrated sulfuric acid, that it has water in it. So when we talk about sulfuric acid, always recall hydronium ion, because sulfuric acid and water can react with one another and form hydronium ion. Okay, so the pKa for hydronium ion is -1, and pKa value for sulfuric acid is -10. So obviously the reaction favors formation of hydronium ion. So to show that we are using acid as a catalyst, you may see that it is written as H3O plus hydronium ion or H2SO4 and water. So they are identical basically. Whether you see hydronium ion or H2SO4 and water, they are catalyzing the same kind of reaction. Now let's look at the mechanism for acid catalyzed hydration. So the first step starts with the alkene and the hydronium ion. So hydronium ion is a good source of proton and alkene is a good source of electron. So they are going to react with one another through acid and base reaction. So the first step is a proton transfer step, and the proton will be added to the less substituted carbon to form a more stable carbocation. So since we are forming a carbocation here, we need to consider the possibility of rearrangement. If carbocation can do rearrangement to become more stable, it will definitely do it. Now, here we cannot do any rearrangement, so this carbocation is pretty stable. It's a tertiary carbocation. Now, the water molecule that has left in the first step will act as a nucleophile and attack the carbocation to form this product. So oxygen with 3 bonds is positively charged. Now this is the molecule that we have, and we want to get to this. So in the next step, another molecule of water will act as a base and take the proton. So this step is a proton transfer step to form the product and regenerate the catalyst. So hydronium ion was our catalyst and we are reforming it at the end of the reaction. So that one was catalyst. Now this carbon is not a chiral carbon, so we don't need to show stereochemistry here. However, if it was a chiral carbon, we have to show wedge and dash to show the racemic mixture of product. Let's look at another example here. So this is an example of intramolecular reaction where the reaction is happening within a single molecule and we form a ring. So as I mentioned before, sometimes instead of hydronium ion we can write sulfuric acid and water, but it's the same concept. Now let's start drawing the mechanism for this reaction. So since this reaction is happening in acidic condition, we are not going to form a base. Meaning that if you think the pi bond will attack this proton and take the proton and forms the oxygen negative as a base, it will not happen. Because we have a solution full of acid, so you cannot make a base in a solution full of acid. Therefore, what's happening here is we have the hydronium ion. So in the first step, pi bond, similar to previous steps, will attack the hydronium ion, and through proton transfer we are going to form this product, and hydrogen will be added to the basically less substituted carbon to form the more stable carbocation. Now oxygen will act as a nucleophile and attack the carbocation. So this will find itself before another molecule of water attacks the carbocation. And we call this kind of reaction intramolecular reaction. So always intramolecular reactions are faster than intermolecular reactions, which happens between two different molecules. Intramolecular reaction happens within a single molecule. Now let's number all the atoms here so we can keep track of that. So we have 6 atoms. We are going to form a 6-member ring. So oxygen attacks the carbocation. And we are going to form a 6-member ring where one of the members is oxygen. So this is 1, 2, 3, 5 and 6, and we have 2 methyl groups on carbon 6. So don't forget, oxygen still has the proton attached to it. So oxygen with 3 bonds is positively charged. Now a molecule of water will take the proton. So the last step is a proton transfer step to reform the catalyst and the product. As I mentioned before, if in the product we are forming a chirality center, we are going to get the mixture of R and S product or a racemic mixture, because the intermediate in this reaction is a carbocation. So let's look at this example. Now if we add acid to this alkene, we are going to get a mixture of enantiomers, which is a racemic mixture. Okay, now let's look at the mechanism here. So again, in the first step, we have our proton source, which is the hydronium ion, and alkene is the source of electrons, so a proton transfer can happen to form carbocation intermediate. So the proton will be added to the less substituted position to form the more stable carbocation. Then in the next step, water molecule will act as a nucleophile and attacks the carbocation to form this product. Okay, and then in the next step, another molecule of water will act as a base and takes the proton to form the product. So in the product, and of course we are regenerating the catalyst, so I draw it right here, H3O plus. So in the product, if you look at this carbon, it's a chirality center. Therefore, we need to show wedge and dashes. So this is one enantiomer, and we are going to form the other enantiomer as well. So it's a racemic mixture of products. Now let's look at the same reaction in alkyne. So here is one difference, and that is alkyne can undergo reaction slower than alkenes due to formation of vinylic carbocation. This is the structure of vinylic carbocation. So alkyne has two pi bonds. One of them will do the reaction, so you get the positive charge at one side of the double bond, and that positive charge cannot be stabilized. It cannot participate in resonance. So due to formation of this very unstable intermediate, the reaction is happening very slow. Now to compensate for that, we are going to use another catalyst, which we call that mercuric sulfate, which is HgSO4. So this is mercuric sulfate. So we are going to use this catalyst to speed up the reaction. So therefore, when the alkyne want to do hydration, we have sulfuric acid, water, and tiny bit of a catalyst, which is mercuric sulfate. So in this process, one of the double bonds react to form the Markovnikov product, meaning that the hydrogen will be added to the less substituted carbon, and OH will be added to the more substituted carbon to form the product, which we call that enol. So the name comes from en for alkene and ol for alcohol. So we have OH on a double bond, and we call that enol. Now enol is not a major product. It's pretty unstable, and it converts to the ketone through the process which we call that tautomerization. So through tautomerization, and enol converts to a ketone, which is the major product, which is the most stable product. Now ketone and enol, they are not resonance structure. It's a big mistake that you think that they are resonance structure. They are two different molecules. If you remember, in resonance only electrons moving, but here hydrogen is moving between two structures. In ketone, hydrogen is connected to the carbon. However, in enol, hydrogen is connected to oxygen. And as I mentioned, 99% of the time you are going to see the molecule as a ketone, not enol. Now why is that? Why ketone is more stable than enol? The reason behind that is that CO bond is a stronger bond than CC double bond. And that's the reason majority of the time we see the molecule exist as a ketone, not enol. So let's make a note of that. carbon oxygen bond is stronger than carbon-carbon double bond. And that's the reason the ketone is always more stable than enol. We have a couple of exceptions that enol is favored, not the ketone. In the first example, we have a diketone, so it forms an enol, and the enol part will interact with the oxygen in the carbonyl through hydrogen bonding, which stabilizes the molecule a lot. Also, a conjugate pi system that forms through formation of enol stabilizes the molecule even more. So there are two factors that can stabilize this enol. First is hydrogen bonding, and second is formation of pi conjugated system. Another example is phenol, because upon formation of phenol, we form a pi conjugated system in a ring, and we are also forming an aromatic compound. So, and there is a lot of stability in aromatic compound. You are going to learn about this type of compounds in organic chemistry too, but for now, know that the reason the phenol is very stable is because of aromaticity and formation of pi conjugated system in a ring. Now, how does tautomerization happen? This happens in acidic or basic conditions, so you cannot isolate an enol. Generally, as soon as the enol forms, it will convert to the ketone. Now, let's look at the acid catalyzed tautomerization. So we have our enol and hydronium ion, which is our acid. Now the pi bond in enol will act as a base, so attacks the hydronium ion. It's a proton transfer here, and the proton will be added to the less substituted carbon. So we are going to form this product, this carbocation. Now this carbocation can do resonance, so we are going to see resonance here. To form this structure. These are resonance forms. And then in the last step, another molecule of water will act as a base, do the proton transfer to form the ketone product. So this is the ketone. So we started with the enol and formed the ketone in acidic condition. Now let's look at the basic condition. So in the basic condition, let's draw our enol. we can have a base such as hydroxide. So the base will attack this proton, removes the proton. So again, we have proton transfer here to form this intermediate. Now this structure, we have allylic lone pair, so it can do resonance. Okay, so we are gonna form this resonance structure, and then in the next step we have water molecule. So this carbon will act as a base and removes the proton from the water to form the ketone product. So again, we form the ketone. So it doesn't matter whether you do this transformation in acidic or basic condition, the result is the same. So we are going to get the ketone at the end. So if you form an enol, you always should think about tautomerization, unless it's one of the exceptions that we talked about. So if the reaction is asking you to draw the product of hydration of an alkyne, you should draw always a ketone, not an enol.